now we're going to look at a very specific system, namely the block oscillator, the block on the end of the spring, to get a better understanding for what we mean when we're talking about this simple harmonic motion. So what exactly do we mean by simple harmonic motion? Well, let's see what we mean. The block oscillator, the block on the end of the spring, as we know, obeys Hooke's law. So we are going to see, we haven't proven it yet, but we are going to see. So we're taking it just on faith. But the Hooke's law, F equals minus kx, form of a force, always will lead to what we are going to now talk about as simple harmonic motion. Well, the mass on the end of the spring, we are going to pull to the right to begin our analysis. So we're going to bring it to a stop at its maximum x position, and we are going to call that the amplitude, and not just the amplitude, but the positive amplitude, because our x equals 0 is the original position where the spring is unstretched. Now, in the absence of friction, so simple harmonic motion has to have no forces that are going to damp the oscillation out, and it can't have any forces that are putting energy in to drive the oscillation. So no damped oscillations, no driven oscillations. What we are going to now learn as simple and harmonic, in harmony. We'll talk about that in a moment. Motion. So when we release the block, the mass is going to move to the left. It will pass through the center, have its maximum kinetic energy, begin to slow down, and will eventually come to a stop out here at its negative x max position, which we are calling the negative amplitude. So please pause if you have to. Make sure you get this page of notes annotated very well. What we are looking at in the graph or diagram here below, we can think of, and I have it here, and please get this into your notes, that we want to think of it as an actual photograph of data, meaning that if we could take snapshots of this mass as it was in motion. So if we started the block out here at rest, so as I have here, we're taking this to be our time t equals 0, where we start our stopwatch. The position is at plus a, and we release. So let's say that it's a certain time interval. So every, whatever it is, 1/10 of a second, whatever, we take a picture and the object is here and it has a speed to the left. Another 1/10 of a second, the object is here, it has a greater speed and is to the left. And another 1/10 of a second, it's here, its maximum speed is to the left, and then it begins to slow down. So it's kind of like a strobe type photograph thing we're looking at. We strobe the light, and we get a photograph every time the light shines, and we can think of this then as data. So if you look at the profile of this data, and if we took the data and we put it into a graphing program and matched it to a best fit curve, we would see that that graph, we would have to turn our paper sideways, but that matches a cosine function. So the data, the empirical result we get when we release a block attached to a spring and let it oscillate back and forth on a frictionless surface, would be matched to this equation. We are going to take this as our starting point. We're going to do a proof to prove that it works, that it does satisfy the conditions for our force, right? That this force matches this equation. We're going to do that mathematically. But for right now, let's just take it as a data fact, that we took the data and this is what we got. Well, we can now understand a little bit about the language of simple harmonic motion, right? Simple because it's not damped and not driven. Harmonic because, as we said, we now have a cosine wave or a function, and we can think of it as kind of perfect harmony. Same amplitude, right? Same amplitude, same pitch. We don't really use, pitch is more for sound than a block oscillator, but pitch is frequency. The frequency of the oscillation, remember, is 1 on the period. So frequency is 1 on the period. So the amplitude and the frequency do not change. We're in perfect harmony, simple harmonic motion. Well, notice that we've introduced a rotational variable. We have omega. So we know omega, right, equals 2 pi f, right? So omega equals 2 pi f, and we can certainly see where the f comes from, right? The frequency, 1 on the period, the number of cycles per second that this oscillator undergoes. And just to remind you, one complete oscillation is from start point to start point, right? That would be the time corresponding to the period of motion for one oscillation, and the frequency then is 1 on that period. So oftentimes, it is not easy to first look at this system and see exactly how we're relating an angular quantity to this linear motion. So again, we're going to see that. I had it in an appendix, but we're going to look at it on our next page, actually page 3 of our notes. So that will be our next lesson, to reconcile how it is this rotational motion can be mapped onto our linear motion, so that our mathematical equation with a rotational variable in it actually makes sense. So again, make sure you get all these notes down. We're going to continue to talk about phase and phase shift to remind you of your trig a little bit before I leave this lesson. The phase of the cosine function is this whole bracketed term. That's the phase. The phase shift is that phi on the end. So that angle will correspond to what is called the shift of the function, and I will remind you of that. We'll go over that to remind you of your trig phase shift knowledge and what that means. So again, please pause the video here, get everything down. There's kind of a lot to unpack here as well. And it takes a little bit of time to get used to it, so please make sure you take complete notes.